This is our second video on fixed effects models. So we have, in our previous video, we did the one-way analysis of variance for fixed effects. Now we're going to do a factorial model. Factorial model is just a fancy way of saying we're adding a second factor. Instead of having one factor, last time we did sports and distress, so our variables was type of sport. We're going to see if there's a difference of type of sport on psychological distress. Now we're going to add in a variable called selection status. So previously we used one independent variable. Now we have two. We have sport as independent variable 1, and we will use selection as our second independent variable. And our dependent variable will still be psychological distress here. Let's go ahead and put those into our model. So in our last video, we did a one-way ANOVA, as I described, and I'll go ahead and reset everything here. And I'll put psychological distress in as our dependent variable. I will then put in type of sport as our first fixed factor, and selection status as our second fixed factor. Again, I'll just remind you all later on, we'll do random factor models, random effects models later on in the semester. Well, shortly. So I'm still going to ask for plots. I often ask for plots both directions, and the reason why, so I'm going to ask for plots, I'll show you when we get to them, but I'm going to do sport by selection and selection by sport. It's effectively the same chart, but it's the graph, the plot, but it shows you it from a different perspective. Sometimes it helps me make quick decisions about whether there's interactions and what the main effects are. So that's why I do that. Your textbook just does one direction here, which is fine. Post hoc comparisons, we're going to do a Tukey's test. We'll do it on both of those individually. I can show you how we can tease out of SPSS. We can, do a little bit of quick cut and paste programming to get a little bit of some interaction effects in more detail if we want that. But for now, I'm going to hit continue. We can do the same thing for our displaying our means here. So we'll go ahead and select all of those. Click OK, continue. We will do residuals just like we did in our previous video. I'm going to click continue. And our options, so a lot of these I'm kind of going through faster because if you were in my last video, I spent a lot of time. Descriptive statistics, effect size, observed power, homogeneity, and some of our plots. Spread homogeneity variance and some of our plots here. Looks pretty good. So we're basically doing the same thing we did with the one-way analysis of variance, but now we have two factors. So we're going to have what we call in class and in our actual lecture videos, non-SPSS videos, we talk about main effects, the effects of each factor individually, and each variable individually, each independent variable. And then there's an interaction sometimes, how one variable might change relative to being a level of another variable. So let's take a peek at main effects and interactions. Click OK. All right, now we can talk more about it from our data point of view. So in class, of course, in our lectures, we talk about how to compute more of this, but here, this is more about our outcomes. I love this warning, little warning we get. No post hocs are performed when there's less than 3 groups. And if you remember, when you have less than 3 groups, if you just have 2 groups with an analysis of variance, it's basically the same thing as doing a t-test. So you know which direction, just by looking at the means, what direction the significance is, if that variable is significant. Basically, you've just done a t-test. So let's take a peek. First, we come up to our descriptives. This is descriptive statistics, and we have them broken out by type of sport, and then within type of sport selection status, we can say overall movement, its total mean is 11 individually for selection versus deselection. We can see a difference of 15 and 7. Just eyeballs, that seems pretty big there for me. And then some of these differences, I can kind of go down and I start to see that there might be visually some differences. Also, standard deviations in general seem to be relatively similar. We see we don't have any issues with that. When we take a look at our Levine's test, we're pretty happy to see that our Levine's is not significant here. So that's our general descriptive statistics, our means and standard deviations, also I guess our sample size. And We see this, sometimes we call the individual level here the sort of cell level, so territory by selection or fielding by deselection. We look across, we consider that sort of the cell level. And let's go down and take a look at our analysis of variance table. So just like we did with one-way analysis of variance, we now have a factorial model. We have a two-factor model. So here it's more important we really focus on what is meaningful that we want to use from our model. First, we have the main effect of sport and the main effect of selection. That's really similar in a way to what we did with the one-way analysis of variance. We also have an interaction effect. We have sport by selection. So those are going to be sport, selection, and sport by selection. These F values here, those are going to be the F values we care about, these three F values. Now our error term, the within term, is still called error, and our corrected total is the total that we'll care about for our models. So just, the error is the within, that's the within group sum of squares. When we look at sums of squares for corrected total, these gives us our corrected degrees of freedom. We should be able to add these things up. So we should be able to see 24 plus 3 is 7, plus another 3 is 30, plus 1 is 31. And that should add up to our corrected total, and it does, of 31. Same thing with these sums of squares. They should also be additive. We should be able to add all up our sums of squares that we care about: sport, selection, sport by selection, and error, and it should equal up to our corrected total, and it does. And remember, we can just kind of go across, just like with the one-way ANOVA and the factorial models. We can kind of go across. We computed sums of squares. We have degrees of freedom. Remember, our degrees of freedom for between effects for the sport is we have 4 different groups. So it's degrees of freedom are number of sports, number of conditions there, which is 4 minus 1. We only have 2 for selection, so it's 2 minus 1. Here we can kind of cross multiply these two together, and we get 3. And that's how we calculate our degrees of freedom. Error, degrees of freedom error, slightly more complicated. We talk about it a little in class, but really it's just the total n, which in this case we can see is 32. We can see that we have 32 people total. We can take our total end of 32, and we sort of lose 1 degree of freedom per cell. Well, we have a 4x2 model. We have 4 different conditions of sport. We have 2 different conditions of selection. So 4 times 2 is 8. So we have 8 individual cells. You could be in sport condition, so you can be in the movement condition in selection. You can be in movement deselection, target selections, target deselection, all 8 of the possible conditions you could be in. So that's minus 8. So 32 minus 8 is 24. And that's where we get our error degrees of freedom from. Our mean squares, we can take our sums of squares, 738 in this case, divided by 3, and we get 246. We can do that for each one of our mean squares. We can just go across the table, sort of put the dividing line right in here, and we can see that we have our mean squares computed. Our F terms are just ratios. For our fixed effects models, this will be different later on this semester, but for now, for our fixed effects models, for each F test, we can take the mean squared of the effect, in this case, the mean effect of sport, and we can divide it by error. It's error term. So we would take 246 divided by 11, and that would end up equaling this 21F. And we can do that for each one of our F scores. We can take the mean squared of 712 and divide that by 11 and get 61. Then we can take this 7 divided by 11 and get this 0.63. We can just see that F, we know F's really can't be lower. They're expected, when we think about expectation math, we know that if we were to go look up the table, there would never be an F value that we would see for our 0.05 level that would be below 1. So we already know that that interaction effect is not significant, and that supports it there. That interaction is not significant. These are significant. We would report those for sport and selection. The main effect of sport, being in a sport, is significant. Being selection is significant. There's not an interaction effect that we're gonna necessarily see. So our main effects, we also can take a peek at partial eta squared. If we wanted to, we could go back and compute omega squared or partial omega squared, sort of do the hand calculations that we talk about in class. And we'd also see observed power here. Observed power is almost perfect. It's 1. So that's the power. So if we wanted to know how powerful our test was to detect mean differences, well, there it is. It's almost perfect. And our eta squared is pretty reasonably large. We can also see that our overall R squared, that's sort of like just kind of use this as a, for later on in the semester, especially when we get toward doing a little bit of, introduction to regression. This R squared is sort of the ratio of sums of squares between divided by the sums of squares total. It's also kind of the classic R squared we see in a regression model, how much variance is accounted for in the model. So we can sort of talk about that overall. 0.842 is how much variance is accounted for in the model. We have our estimated marginal means again. I'm just going to click through those relatively quickly. This is where if we wanted to, we could get a estimated marginal mean and its confidence interval. We'll also see these things plotted a couple different ways. Go. Here is our post hoc test. We did ask for Tukey's test. These only shows the Tukey's test for now. I'll kind of tease some other stuff out later. So I can show you an example as if we might have had interaction effects. But we can see that we only have the multiple comparison procedure for Tukey's test for type of sport, and that's because we're only looking at main effects here. There were only 2 levels of selection. So when we look at selection, when it says selection is significant, well, the only option here when we look at selection is significant is its overall main effect of selection of the mean of 23 and the mean of 13. That's where the difference is. So we don't need to do an additional test for that, but for the main effect. But for our multiple comparison procedures here, it's just like we did for the one-way ANOVA. We go through each one of these. We can see movement is different than all 4 from a significant standpoint here. Target, we can see where there's significant difference from movement and territory. And also remember, only half of these should ever be reported, right? And only report really the ones that are significant. That's typical procedure. You may report a table, maybe, but again, when we look at movement versus target and target versus movement, we just see it's the negative in the numerator here and the positive in the numerator here, but it's the same exact test. And just as a quick reminder, all of our multiple comparison procedures are really just some sort of mean difference we calculated. In this case, it's based on just raw mean differences versus some sort of standard error. Again, calculated, I showed you in our last video that we just pull from the mean squared from our table. Mean squared error, here's mean squared error of 11.53. And they're using mean squared error of 11.53. And then they're adjusting it. Again, they're using the harmonic mean. In our hand computed examples, we might compute ours slightly different to actually compute the standard error. But here's the significance. And then the homogeneous subtest, these sort of tell you which ones are sort of not different from each other. And gives you a quick eyeball test on which ones might be pulled together. That in our last video. And I was going to show you one more thing before we move on to a couple assumptions. This is a plot of our estimated marginal means versus type of sport. And when you see parallel lines, or lines that are roughly parallel, you tend not to have an interaction effect. You can also see that regardless of which of the groups, which of selection versus deselection, there's general increasing. So there's sort of a main effect, regardless of being selection or deselection, general increasing. Well, that's also a hint that there's a main effect potentially here, but not an interaction. I also mentioned to you, I like to do it both ways here with my sort of plotting my estimated marginal means, because now I can see that there's really relatively parallel lines here as well. So there's not like a trick of the eye, no, interaction effect going on. And that between selection and deselection, this main effect here, that you decrease regardless of which group you are from selection to deselection. So that's pretty interesting sort of to see those two charts graphed both ways. I just have a tendency to do that for myself. I would only report, if I were reporting this in a journal article when I go to publish, I'd only pick one of those two. I probably would pick the first one of those charts, and that's what I would use for my publication. Our textbook tells us how to tease out some interaction effects a little bit more. I'll go ahead and do that actually for us. Why not? So when we go to do we can kind of go all the way back to our steps, and it's already SPSS already by default has all this stuff for us. I'm going to go to the expected mean squares. I'm just going to put in selection and sport by selection in here. I'm going to ask for it to compare means, and I'll just do the LSD test. Actually, your book does the LSD test here. I actually prefer the Bonferroni test of comparison. But for consistency, I guess I'll go ahead and select that. Instead of running this, I could just go click the button now and rerun this. But instead of doing that, I'm going to click paste. All of the code that actually SPSS runs, SPSS syntax, is produced for me. I am going to modify one line of code, just like your book does. We're going to see this line of code here that's going to produce the interaction of sport by selection for my expected mean squares. Well, I'm going to also ask it for compare. Spell it right. And I'm going to ask it for sport. Make sure that's spelled. Case. And we'll ask it for the LSD test here, just for consistency. We could ask for the Bonferroni. If I were publishing this, I would ask for the Bonferroni instead, but for now it's fine, just for consistency with the textbook. What's cool is that we could change any of these things. We could change the type of sums of squares that we use. We'll talk more about that later. We could change what type of post hoc comparison we used. We could change profile plots. We could change other things about our estimated means. We could even change the criteria for alpha. So it's kind of neat to see sort of the back engine of SPSS syntax. I'm going to go ahead and run this. And the whole reason I'm running this is just really so I can pull out it's as if I had a significant effect, so I can sort of get to a more granular cell level comparison for my model. I'll go ahead and run all, and if it runs correctly, everything should run the same, except when I go down, I should have a table. Here we go. I have a larger pairwise comparison table. So now I can look at movement, target, fielding, and territory comparisons within selection. And I can look at movement, target, and fielding territory within deselection. And we can see within selection, are movement and target significant? And the answer is yes. And within selection, is target and fielding significant? And we can see the answer is no. So this is kind of cool. This is like if you wanted to do cell level interactions. What I also like about that is that then maps sort of to what we're looking at here. We can sort of see it, these are sort of paired comparisons in space. We can see that within selection, what are the difference when we plot those different means of those groups? And within deselection, what's the difference? We see the same thing here as well. Within selection, the differences amongst the means, and within deselection, the differences amongst the means. Well, this chart, this comparison table really just shows you the details and whether what your eye is seeing is significant or not. Go back to our data, we'll see. We have two residuals here because we ran their model twice. The second time when I ran everything with SPSS syntax, we can just delete one of these. You see they're identical. It's just I ran the model twice. So let's go ahead and delete one for clarity. And I'm going to go to Analyze, Descriptives, and we'll do some exploration here. We'll just explore our residual. Now we can explore our residual just as an overall residual, just like we did before. Let me cancel that. And we'll ask for histogram and some plots. Won't go over every one, but go over a couple of things. I'm going to click OK, and then I'm going to come back here. Well, let's just click OK. Right, take a peek at a couple of these first. we can see that when we run the overall, we get our overall skewness and kurtosis that we might want to report, that you'd report in your as your overall test of normality. And then we can do the same thing when we do by sport and selection. And I think I'll go ahead and just click OK. Even if it's sort of the reverse order, that's okay. So we see that we now have our movement. This is overall for type of sport. And if we go down, and we can see, we can check to see those, that we have overall for, let's see, it should be down here, and we get a lot of our same stuff we've got for overall for selection. Now your textbook shows you, I'm not sure if they do the sort of coding here piece for you, but we'll go ahead and do that anyway. The textbook shows you, example of like the cell level. So what we actually want is the type of sport, movement, target, fielding, and territory by type of selection status, which is deselection and selection. So just like we did for, we can sort of we're cheating the code here. We're pasting code instead of running. So I should have pasted to our same syntax editor. We see that when we examine, we're examining variables, we're examining by, sport, and selection. Well, one of the things we could just do, copy, paste, and create sport by selection. Now, that should work there. We'll see if I have to actually use by. I will highlight that, and I will just run, instead of running all of my univariate model before, I'll just run this subsection. We'll go down. It's going to produce here we go. So we have our, it's just our first one from last time. Should be our third one up. Here we go. It's a big table, but we have type of movement by selection and deselection. So we can go movement, selection. We can look at the mean. Of course, it should be 0. We can look at the skew and kurtosis, 1.4, and we see kurtosis is 2.031. We can map that up to our textbook. I won't go through each one of these, but you can see that we went ahead and did that. And we also have, if we wanted to, the analysis at a very granular level. The analysis is at the cell level. It's at the level of, we have 8 different cells. That is, we have a 2x4 model. We have 2 levels of selection and 4 levels of sport, and we can examine our normality in each one. I guess since we're getting a little long on this video, the last thing I'll do here is go back to the data, and we're going to split a file. We're going to split the file so we can take a quick peek at independence. We've looked at normality, homogeneity, and variance. We've looked at our assessment overall. We've got a bunch of different graphs we've produced. So let's take a peek at independence here and the way that we do in our textbook. Again, I'm a big proponent of, when possible, relying on both logical arguments and statistical arguments. But we also sometimes need to support that with some of our mathematical arguments. So before, when we ran our model, we just ran it on sport. We did distress. We broke it up by sport. We took a look at the residuals. We take a look at the residual of distress by sport. Now this time, what we could do is we can split our file. We could split our file either way, by either of our independent variables, and take a peek within each of those to see whether or not, based on whether or not there is independence or not. So we'll just go ahead and do it by sport. I think that's what your textbook does. This is an example. So this is kind of a cool thing to learn anyway. We can split file. If we go to data and we go split file, we can say, okay, let's organize our output here. We can pick either compare groups or organize by groups. I'm just going to select organize by groups, and we're going to select sport. There we go. And then I'll click OK. Now, any analysis I run right now would actually be run with that split file. See, I have split by sport. So if I run analysis of variance, it actually would run it, breaking it up 4 times, once for each of those sports groups. So now, though, what I do want it to do is I'm going to go back just like we did before with our graphs. I'm going to go to legacy graphs. We're going to do scatter plot. see if I even take, oh, I had support in there before. Now I'm going to take the residual for distress, and then I'm going to select our selection status. Make sure not to select sports because you won't get a model because it's already broken up by sport. So then I'm just going to click OK, and I should get 4 tables. There we go. I could go through, I'm not going to do it this time, and put the line here for 0. We can see these are kind of randomly scattered around 0. These normal, nothing really is surprising. I don't see any weird pattern. They're a little different, but they're all kind of distributed around 0. We don't see all of them, sort of doing anything strange. There's other analyses we could do in R, but for now, this is one of the main ones we're doing, just to kind of give ourselves an eyeball test of whether or not independence exists. And I don't see any odd clustering. I see scattering around those zeros. Well, I'll sort of leave some of this for you to play the at-home game with me. So like when you go and look in your textbook at our examples, we have the research template in the back of our chapter. When you go to chapter 3, you look at the examples and the example write-up. In that section, when we start looking at all of those assumptions of normality and independence, we look at Levine's test. We can see that the Levine's test in the back of our book has a 0.579, and we see that that's replicated here. When we go to look at our scatter plots, we just did that for independence and normality. We took a peek at our kurtosis and skews. We're putting those values in just like we would in our one-way analysis of variance examples. Further, when we're reporting, maybe most importantly, when we're reporting our F-tests, when we see in our template that the interaction was not statistically significant, but there are statistical main effects. Well, this interaction is sport by selection. It was significant, and the F value is 0.631. I'll notice that might be an error in the text, but we also would report, this is the correct value. We would report degrees of freedom with that associated as 3 for our interaction effect, and 24 because we have, this is our interaction effect with 3 degrees of freedom, and our error term is 24. Actually, our error term denominator is going to be 24 for each one of them. For sport, the main effect, we had this value of 21.35. So our F equals, for a main effect there of 21.35, we can see degrees of freedom are 3 and here and 24 here. And we could report this 0.00000 thing as less than 0.001. And same thing for selection. Selection had a large F of 61, and it was significant at the 0.001 level. We can see that degrees of freedom were 1 for our between effect and 24 for our error term. Effect sizes, if we wanted to report eta, I often report partial eta squared. Actually, I always report. I always get asked, even if I convert it to omega, I always end up getting asked for partial eta squared. So I might report this 0.727 for sport and 0.720 for selection. I'd also report the 0.73. If I reported nothing else for sport by selection, saying it was not significant, I would report the effect size, saying how, what size the effect was for the model. So I think it's a lot. I mean, we could also talk about power. Power is perfect. It's just about 1. We had a low power here. We had a small chance of detecting the difference if it actually existed. So those are the things that we would place into our templates, and we can kind of go to our template in the back of our textbook and match all of those things up and see how we ended up, reporting on our assumptions and reporting our analysis of variance. And then eventually we'd bin together and we would report some of our post hoc comparisons, whether they were at the cell level or at the group main effect level. And with that, this video has gone long enough. I'll leave it at that, and hopefully this will help you with your next assignment for factor models, and also for our factorial analysis of variance for fixed effects models. And also, I hope it just kind of helps you with some walking through of SPSS in general.